Thank you very much, everybody.
Closer to your mouth. We can't hear you.
Pleased to be here at this correspondence of the what is it, CNPS, right, 2016. I'm going to focus on the gravitational deflection at the sun, in particular, at the sun, not only the stars, but also the sun-like stars in our region of the galaxy. And what you will notice that over a period of time, at least the past 100 years, most of the gravitational lensing has been observed at the plasma limb of the sun and of the stars, if that is altogether possible. But however, the gravitational lensing has been always historically observed at the sun. And when you take systems like satellites and you put them in deep space, most of our systems communicate using microwaves. These are centimeter wavelength systems. And as centimeter wavelengths, or the frequency of microwaves in particular, from 8 gigahertz down to 3 gigahertz, these systems resonate with plasma, especially the plasma limb around the sun. And what you'll find out that when you have microwaves from extragalactic radio sources, these are extragalactic systems which are primarily very dense objects that emit microwaves, and these are mostly extragalactic systems. And these systems are very powerful radio sources that emit very intense microwaves on a very defined frequency. And these microwaves, when they come from distant sources far away, what you notice is that if you are far away from a source, and the waves happen to be propagating in this direction, and far away from these sources, all the rays are parallel to one another for all practical purposes. But what happens is that when you observe these sources, and these sources are so way over here someplace, millions of light years away, what happens when these waves pass by stars in the sun, they tend not to be lensed at all. And that's a fact. That's a fact of observational evidence. When you look at this and study it, the only lens that they find is that when these rays come in tangent and interfere with the solar plasma of the sun, and they are lensed or bent. And this bending is, you take this equation, you can derive this equation using classical physics. You don't have to use relativity to get this, but I'll show you how to get this equation. I managed to make a publication, and I published this same equation derived using minimum time energy deflection. A path of electromagnetic waves will propagate in a plasma. You're on a path that is minimum energy or least time. And you teach our students in graduate physics and graduate studies to calculate this in mathematical physics when you use Occam or some other magnetism or Weber's electromagnetism. They learn to calculate the minimum energy path, and you get the same equation. What happens when this wave is tangent to the solar plasma limb of the sun, there's lensing and it's bent down exactly 1.75 arcseconds. And the wave that comes here at the bottom is lensed up 1.75 arcseconds. But it turns out there are some scientists and engineers who have a dream of using the sun as a lens or a distant lens to send a satellite far out into space, going away from our present location to 550 astronomical units. These rays will come together and come to a point. That is 550 astronomical units away. That's about approximately 17 times the orbital distance of the planet Pluto. That's quite far out there. So you can put a satellite out, and what you do is you look back at the sun, and you'll find, when you look back at the sun, you'll find that any star that's way over here will have an Einstein ring around it. So you have to get away from the sun, at least that distance, going out into space. So let's go forward, and I'll show you what I mean as we go forward. And I'm going to show primarily pictures, and there won't be much mathematics here, but you will see from the picture that I'm talking about here. The significance of what I'm talking about, you have the significant findings. You have solar gravitational gradient. There's a solar gravitational gradient that acts on the gravitational gradient of the sun. That solar gravitational gradient, because of the gravitational field of the sun, will act directly on the solar plasma limb. And vice versa, the solar plasma limb will act directly on the electromagnetic waves propagated within the solar plasma limb. But however, the first one, the solar gravitational gradient, does not act directly on the electromagnetic waves, it acts indirectly on the electromagnetic waves. So what you have an indirect interaction, but not a direct interaction. And that's the finding that I found here on my research and the publications that I have made thus far. And I managed to publish in some peer-reviewed refereed papers, and I'll have you give you copies of these papers. So let me show you an illustration, a diagram of what we are talking about here. You have the gravitational gradient field of the sun acts directly on the plasma limb of the sun. That's the direct. Here's the plasma limb, now where you have the particles and the atoms in this region, or because of the intense thermal energy of the solar line, we're talking about approximately 5,000, 6,000 degrees Celsius. The atoms in this thing are totally ripped of the electrons. So you have nuclei which have been ripped away of all of its electrons, so you have positive and negative atmosphere here. That's the plasma, pure plasma. And you can calculate, because of the gravitational gradient field of the sun, you can calculate the minimum energy path of radiation going through this plasma. And what you come up with is 1.75 arcseconds. Because of the effects that it shouldn't be any surprise at all, because most of the lensing and the gravitational deflection has been observed in the plasma limb of the sun. But the rays propagating way out here, going out into deep space, going away from the plasma limb of the sun, these rays tend not to be affected at all, at least in the microwave region, not affected at all by the gravitational gradient. So let's go on and we'll talk about that as we go forward. This is what we observe. What we observe has been for the last nearly a century now. You find that these rays out here, the electromagnetic rays propagated in plasma free space all over, right? In our observational space is not lensed at all by the gravitational field of the sun. That's the gist of what I'm going to be talking about as we go forward. Here's what we have done experimentally. You can set up experiments and put in space, and what you have is a long path interferometer. And you can put a satellite up, and if you have the sun, and you have an array, a source of emitting microwaves in this region going far away in this direction for millions of light years away, extragalactic sources that emit microwaves. These microwaves here are not affected by the gravitational effect of the sun. But however, if you place a satellite and let it move in this direction, going in this direction, what you'll find out, when you pass down through this region and you detect this ray, you will notice this ray has been deflected 1.75 arcseconds downward. So you have a negative sign here and you get a negative pulse. Going down further, there's no signal because all the emissions coming from these stars have been blocked by the sun, so there's no signal here at all. But down here, you get another signal. You find that this ray has been deflected upward, so you get a positive deflection of 1.75 arcseconds, right? This one is deflected up, and that's deflected down. But if you extend this out into deep space, these two rays will come together to a point 550 astronomical units away, approximately 17 times the orbital radius of Pluto. So this is what you can do. You can take this long path interferometer and do so. And the Earth could be have antennas on board, and these antennas could be out in the field somewhere, out probably in South America somewhere, someplace where you get free of emission of interference. You got to get away from large cities where you have large cities in town. These systems will get interference from broadcast systems, so you want to avoid that. that could be an inner formula. This could be the path of the Earth as it moves downward. And in this satellite system, these quasars, these distant extragalactic quasars, would be point-like sources emitting these microwaves, and you actually detect this. But note here, the most important thing to remember is they get only 1.75 arcseconds deflection. Not one half of that, but exactly 1.75 arcseconds deflection. And not more than that, and not less than that. And the impact parameter is always equal to the impact parameter which corresponds to the gravitational radius of the gravitational limb of the sun. And the radius of the sun is approximately, 950,000 kilometers. And that's the impact parameter, and not out here. There's no bending out here in deep space away from the plasma limb of the sun. Only at the plasma limb. So let's go forward, and we'll talk about that as we go forward. What's important here to remember is that our sun, any star, that a star-like sun with the same mass and the same radius, will have a gravitational potential. The gravitational potential of the sun looks like this. In the textbook, if you go close to the sun, you start out here, and you notice the gravitational potential of the sun is going to go enormously high, very big. If you go away from the sun, the orbital position of the planet Mercury and Venus and Earth, one astronomical unit is Earth. At this position of the Earth, the gravitational potential of the sun is like this. But if you plot this, take this box and blow this box up. If I blow this box up, I have the Earth here at one astronomical unit. Then I have the gravitational potential plotted together with the gravitational potential of the sun and also the gravitational potential of the Earth. It turns out that the gravitational potential of the sun is nearly 14.14 times greater than the Earth. So the sun, the gravitational potential of the sun is very big in comparison to that of the Earth. But that's the gravitational potential. So the sun, nothing outweighs the sun in our particular location in our orbit, at approximately one astronomical unit. But not so if you calculate what is known as the gravitational gradient. That's different. So if you have a gravitational potential, you have this V, right? But you take the gravitational gradient, you have to take the partial derivative of this with respect to Z, the point going away from the source. So let's show you how that works. The gravitational potential gradient is as follows. The definition of gravitational potential gradient is the following. If I take the Earth, for example, and I take the gravitational potential gradient, we can find out what the gravitational potential is by taking the gravitational constant, mass of the Earth, and the distance from the source. That's the field, right? This is the Earth, and this is the gravitational potential of the sun. But however, you notice the sun outweighs, much bigger than that of the Earth. But however, if I take the difference, show the difference between these two is approximately 14 times. One is the sun is 14 times bigger than that. But let's go forward with the gravitational potential. Here you define the gravitational potential as follows. You take the partial derivative of the gravitational potential of the sun with respect to Z. And that Z, that's the distance R, which is one astronomical unit away from us, right? That's the distance from us to the sun. You can take that 1 AU. And if you compare that with the gravitational potential gradient of the Earth, what you find out, the gravitational potential of the Earth is actually, the sun is much less than what the gravitational potential gradient of the Earth is. If you take that distance from the Earth is only the radius of the Earth, and here this is one astronomical unit. Comparing these two, you come up with a surprising difference. You take the distance between the Earth and look at the gravitational gradient potential of the Earth and compare that with the gravitational gradient potential of the sun, you'll find that it's almost 1,000 times, 1,600 times bigger than the sun. The Earth has a very large gravitational potential gradient, And this is the reason why you put satellites in deep space with atomic clocks running on board. The Earth has a profound effect on these clocks, how fast these clocks would run. So this is very important. So I'm going to come back to that in a second to show you the difference here. This is why, to explain why this is important. The reason why this is important, look at the, from general relativity, you take the gravitational bending, light bending, that's 4 times the gravitational constant times the mass, divided by r(c) squared. You can derive this equation using general relativity, but we don't have to use general relativity. You guys have other methods. You come up with the same equation using alternative methods and schemes. But the integrated effect of this, you take the light beam that's coming from a distant star, you find that this bending, because of the mass here, which can have a radius of r, this is a uniform mass, like the Earth. It's pretty much uniform except for the core of the Earth. Most of our planets in the solar system have an iron core, or some core that's very massive. However, let's assume that this is uniform mass, right? There's bending coming from a distant star, and let's call that delta 1. And there's also bending going away. So during approach, a beam is bent around this mass, and going from receding the mass is bent down. So if you take these two and add them up, you come up with 1.75 arcseconds. It's bending, going, approaching, and receding. But guess what? You take this same mass and squeeze it down, make it more dense, right? If you want to make this mass, you can take the Earth, for example, and squeeze it down to a smaller mass, and put that mass inside of a Gaussian sphere that has the same radius of the Earth. What you do, you measure the same gravitational field on board, on set, standing on this gravitational potential surface, right? But by squeeze it down to something like a neutron star, or some kind of neutron particle, the mass of the Earth, the whole Earth, given the theory of what a neutron density is, the Earth could be something less than a basketball, size of basketball, maybe even a golf ball, depending on how you do this. But this particle could be a very small particle, like a black hole or something like that, miniature black hole. Theoretically, that miniature black hole, the same mass as the Earth, could be placed inside of a Gaussian sphere, and the same gravitational potential would be at the surface. You wouldn't be able to tell the difference between this and this mass. That shows you that the Gaussian potential, that the same principle is used when you have a particle, a charged particle enclosed in a Gaussian surface, and that Gaussian surface tells you that the potential at the surface depends on the mass that is enclosed. But gravity has a similar principle as that of electromagnetism, where gravity enclosed in a Gaussian sphere is depending on the mass enclosed. It doesn't care what the size of the mass is. It just cares that it cares about the size of the mass, but it doesn't care what the mass is. This mass could be, as long as it's point light. It doesn't even have to be a sphere. It could be shaped like a wedge or something. As long as this size is very small in comparison to the radius of the sphere, and as long as it's point light, this principle will always hold. So let me go to the next one, and I'll click forward on that. Let's combine this previous slide with the slide which is known as the principle of reciprocity. If I were to look at some star, distant star out here, and you said the lenses are going to take place. This telescope, the observer of this telescope, he sees the source, but he sees the image of the source here. But the source is actually located behind the lensing, but when looking out in deep space, it would be apparent. It is apparent to the observer that the lensing, the image is here, located at this point. Let's say you were to shoot a laser beam back in the same direction. So I see send a beam back in the same direction. It should take exactly the same path going back the other way. That's the principle of reciprocity. And anybody who designs lenses, that principle of reciprocity is very, very important. To design telescopes put up in deep space, we use this principle, reciprocity, to design lenses. You have a system of lenses, and you want to figure out how to best make the best telescope that makes the best telescope that can amplify the signals out in deep space. You use that principle. That works for gravitation as well as light. So going forward, the next one. So comparing this to what we just talked about, reviewing this, take the same principle on approach and receding with light wave. You get both of these added up. So add up to 4 times Gm over r squared. See, this is the light bending of general relativity, designed by relativity. You can design it. You can derive this by general relativity. And this applies to all of these masses. What's constant about these? They all have the same mass, even though this mass may be more dense than the first mass. It doesn't care about the density. What it cares is the quantity of mass that you have enclosed. So, summarizing what I just said in the last 5 slides, is this. If you have a star that is burned out, when a star system depletes all of its energy, it's going to collapse down to something like a white dwarf or some kind of dwarf system. And that dwarf system, it could be the size of our sun when it's brand new. But once it dwarfed down, all that mass could be something probably not much bigger than the Earth. And when this thing collapses down, the gravitational bending should be approximately the same, because it would deplete some of its energy and some of its mass, but probably on about maybe 5 to 10% of its mass would be depleted, but most of the mass is still going to be there. So it becomes a dwarf star, or it could become a black hole if it's pretty size of a star, that is. So, summarizing what I just talked about, we had this system with the Gauss principle of Gauss, and the principle of reciprocity. We use both of these, and I'm going to talk about what I'm talking about here. Let's take a look at what gravitational lensing is all about. Here we have this distant source out here, and it says a red star, and it's going to emit red packages of light. This could be packaged, you want to call them photons, or you can call them electromagnetic packets. And it's dumping out all these waves, and they're going in all directions. These waves are going in all directions. But what happens, I got a massive source right here in the middle where this X is. This is some kind of massive device that is caused from gravitational lensing, and it's predicted by general relativity. Relativity predicts this is going to happen in a vacuum. Let's say the relativity were correct. If that is so, I can place this mass here, and if I place the mass halfway between the observer, which is here, and the source, which is over here, and let's say that the lensing device, or the mass, right here in the middle of it, it turns out that the light bending be such that these rays, these photon packets will come and find its way to the observer, right? Along this path. You can take this path, or you can take this path going down. Both of these paths are reciprocal to one another. I can draw a line between the observer and the source, and I can flip this around, and this curve will flip on top of this curve, and this will be exactly the same. But however, between the observer and the source, if I take the what is known as the line of reciprocity, or the line which defines the symmetry between these two, where I can take that line, this path will be such that this flat, if I flip this curve from here, this point where the observer is, we'll flip around this line, which is the symmetry, the line of symmetry. And this point will go over there, right? So relativity is a symmetric principle when you derive these waves, and that's what they're teaching in the textbooks, and this is very important. So looking at what does the observer see? What does the observer actually see? It doesn't see a point. If this is the case, the observer should see an Einstein ring looking through the eyeball of his lens, and the telescope that he's looking at, he should see an Einstein ring, right? And not a point source, he should see a ring, a red ring. And that's what he should see, according to the prediction of general relativity. So let me go on, and we'll talk about this. The impact parameter, what's so important about this? The main point that I want to make clear here is that when you look out in deep space, and you see all these lensing devices that have been defined as lensing, some of this stuff has nothing to do with relativity at all. There are a lot of objects out there in deep space that can cause lensing. And there's some gas bubbles out there that it's not even matter. It's not even mass. It's not solid mass. It's just a bubble of gas. And gas could accumulate to whereby you can get an enormous amount of gas, the most like hydrogen, helium, and other gases, neon, or whatever. If there's enough gas, it will become more and more dense, and the gas will squeeze down. And if there's enough energy, these particles will squeeze in such a way, if there's enough density, it could ignite into a star. So this is how stars are being born. So stars are being born by these gas particles. So we'll go back, let's go forward, and I'll talk about this. The review of what I just recently talked about, we have the solar lensing produced by the gravitational gradient of the sun. And this gradient is approximately 5,000 to 6,000 degrees Celsius, where you have ionized particles in this rim, or the limb, what it's called. It's a thin plasma limb. And this is one, like you put a Gaussian sphere around this. It has exactly one radius of the sun, right? By increase the Gaussian sphere twice the radius of the sun, instead of having a lensing, which is 1.75 arcsecond, the lensing out here would be exactly 1/2 of this divided. So instead of getting 1.75 arcseconds here, I should get 0.85 in this place here. But if I increase the Gaussian sphere 3 times the radius of the sun, I should get lensing also according to general relativity. This lensing should be 1/3 of 1.75 arcseconds. If I go to 4 times the radius of the sun, I should get 1/4, and so forth and so forth. So what happens is you go further, for increased impact parameters, the lensing should get less and less and less. And this is easy to see with current means of observation, and we don't see that. In our sun, we don't see it at the center of the galaxy. I show how relativity fails. And I managed to put some papers on this thing effect. And relativity theory, people who support relativity are fighting against this. This is what we see. We see the sun causing lensing at the solar plasma limb, right? We see no lensing observed at all out here, no lensing. These waves are coming right by us. And the question here is, main question, the primary question is, where are the Einstein rings? Where are they? So, in summarizing that, we have the lensing at the plasma limb of the sun, 1.75 arcsecond. No lensing here, and no lensing out there. So the light thing is due to the sun's gravitational field, the gravitational gradient acting on the plasma limb. And this is what we observed for the last 100 years so far. Here's a NASA. You can go to the NASA website, and NASA got it, published this. If you go to this website, which is science.nasa.gov, the Science News, NASA at NASA 2004. This has been up since 2004. 25 March, I think, Einstein, people who studied Einstein and lensing at the sun, they find out you have a star here, and that star appears to move, right? And this sun approaches the star, and it seems like the star actually moves, but the star doesn't move. What happens is that you see the apparent position of that star because the light is bending, coming towards the sun, and is coming towards our telescope, and we're looking in an apparent direction of that star, right? But however, theoretically, if this star, if the Earth, if the sun were lensing enough, and if there's a star behind this thing, you should see Einstein ring around the sun. We don't see any of those, and those are not visible. In our region of space, it's not visible. And the question is, where are the Einstein rings? Let's talk about this again, review what we just talked about. So if we have the sun, any star the same mass and radius of the sun, one solar radius and one solar mass. Any star that has one solar radius and one solar mass calls lensing, and that lensing would be 1.75 arcsecond. No matter what the star, so far as we know, all the stars in our solar system, our galaxy, region of galaxy, is pretty much like the sun. There's not much difference between the sun. And the focal lengths F and R of the sun are expressed in the same units. If you express those in the same unit, star in the solar mass, one solar mass and one solar radius will cause lensing, and it will come to a focus at 550 astronomical units. So the focal length of our sun is 550 astronomical units, approximately 17 times the radius of the orbital radius of the planet Pluto. It's the most distant planet. So if we want to do this, you can use this as a lens, a microscope, and you have this star out here somewhere in deep space, and you come out here in deep space and put an observer here. You can use the sun as a lens. In that sun, you can see objects way over here someplace, and it would amplify it for you or magnify it for you. This theoretically placing some kind of observer right out here, and it's been the dream of astronomers to go out in these places and put some kind of probe out here or some kind of observer instrument. Take a camera, turn it back, and look at the sun. You'll see all kinds of stuff far over here. This will work according to observers using the sun as a lens. So keep that in mind. And I won't bore you with the mathematics, but you can do the math and you can go through and look at this. You take the distance of the sun, the radius of the sun, and so forth, the acceleration of force on the surface of the sun, and you go. It's total gravity of the sun is very intense, very intense. But you can take it, the acceleration effect, 1/r effect of the sun. This is what it looks like. And you observe the lensing going out in deep space where you have this radius increase going out in space. There's no lensing up here at all, right? But however, at the limb of the sun, you get this lensing. Is that what you have, according to relativity, it predicts 0.88 arcseconds out here, where you have this distance. But guess what? This doesn't happen. You don't see this at all. So that's a problem. The relativity is quiet about this. They're not talking about. And this is another thing called the Shapiro effect. What this Shapiro effect is that you put out satellites in deep space. Most of our systems in space, we communicate with each other between our satellites in deep space. We use microwaves. And these microwaves, it turns out that depending on what the frequency of these microwaves are, the frequency of the microwave, when this microwave passes close to the surface of the sun is emitting, it streams up. It's a nuclear furnace, and it's ejecting out what is called the electron clouds, right? These are solar winds, and the wind is blasting. You can put a sail in the space, and you put the sail in the right place, and you can use this solar wind, and you can propel yourself through space if you're careful how you maneuver. These winds will put satellites, and they use the solar winds to correct the position of satellite by putting up like an umbrella-shaped device, using the solar wind and the prominence will explode on the surface of the sun, ejecting out all these particles. And some of these things fly by the Earth with supersonic speeds up to maybe 100 times supersonic speed, sometimes 1,000 times supersonic speed. And this is very incredible. It turns out satellites broadcasting signals to Earth, right? You find out there's a delay between this satellite signal going to the Earth, and as this beam comes close to the sun, the delay increases. This is called the Shapiro delay. And the Shapiro delay has absolutely nothing at all to do with general relativity. This is a different effect in the general relativity. Because of this, if you take the satellites on different frequencies, right, have 8 gigahertz instead of 4 gigahertz, 5 gigahertz. This delay depends on the frequency of the satellite. The relativity has failed that already. Relativity does not predict that. The frequency dependent. This is a frequency dependent system. And summarizing what I just talked about, is to summarize that you have this the right bending because of the solar limb, and you have what is known as the Shapiro delay. And this Shapiro delay, this propagation of transit time effect, is both the frequency and impact parameter dependent. They're both depending on frequency and depend on impact parameter, both of them. And that relativity does not treat that possibility. And this is what generally happens. You have light bending of these rays, and this happens in optics, and it happens in microwaves, right? It happens in, so what happens? We have an electron density profile of these particles that are ejected from the sun. This is a plasma system that's ejected out past all the 9 planets of the solar system. So you get this enormous bending, the light wave, the beam coming from the sun. You can have an index of refraction associated with it. As well for optical frequencies and infrared and ultraviolet frequencies, that index of refraction is approximately exactly 1.0, exactly 1.0. But for microwaves, it turns out this is a little bit bigger than 1. Microwaves resonate with plasma, and relativity does not predict different microwave frequencies and so forth. And this is the data which handles that. You go to my website, and I have this on my website. The data and information describes how you calculate that for 2.2 gigahertz and 8.8 gigahertz. And for both of these frequencies, they have an enormous difference between the two. So it is frequency dependent, right? And therefore relativity fails again. Relativity is independent of frequency. It should be, right? But this is not. This is frequency dependent. So here's to summarize out what I just talked about. Most rays coming from distant stars. Let's say you have stars that are so far away up here. If you take these rays and you look at them, the rays that will get bent will hit the plasma limb of this star, right? But the other rays will keep going. There's no bending at all unless these rays happen to coincide with some plasma limb or some star similar to our sun. If this rays come close to this star, it would be bending. If this ray is bent, let's say 4 light years away, the light coming from these rays would be bent away, and it would never reach our telescope. These rays, we will never see this. But these rays, we will see the distant stars from this way because of these rays. But the rays that get scattered or bent by near systems out in deep space become invisible to us, and we will never see any evidence because these rays would be bent away from our observation. That's what happened. That shows you the answer. Reason why you don't see Einstein rings in the star-filled skies. One star right behind another star should have a ring associated with it. The reason why you don't see that ring, number one, it has an impact parameter equal to the star, the radius of the star. It is not bent in deep space because of this. The rays will pass by these stars in deep vacuum space. In vacuum space, there's no bending whatsoever. So the question is, where are the Einstein rings? And that's the answer, where the Einstein rings are. And this is the reason why you don't see the Einstein rings. Because light that goes by these stars and is way above the plasma limb of these stars, it has no bending whatsoever. And this trouble is relativity. That's a problem for relativity right now. They can't explain that. And this data explains that exactly. And here, this is a calculation showing that what I did. I managed to publish this paper, and I calculated using the minimum energy principle. You can derive this equation without using relativity. And that's what I did. You can show there's no direct interaction between light and gravitation. It's indirect interaction only. And on page, you go to my book, on page 12A in the appendix, and 13A, 14A, I showed the calculation using this bending effect, using the minimum energy path or the least time path published in textbooks that undergraduate students can do this calculation. If you give this assignment to students, they can do that. In high school, we'll write students in high school that are already studying mathematical geometry, and also graduate students beginning physics in graduate school. This is an easy problem to do. So what you do, you take this effect, the integrated effect of gravitational field of a mass m, and by integration, say from the radius of the star on out to infinity, going from the radius of the star on out to infinity, start with this equation, and you take that maximum velocity, the escape velocity of a particle going at you have an exploding nuclear furnace on board the sun. And these particles they bound to the sun because of the sun's intense gravitational field, and most likely it's not going to escape. But some particles do manage to escape because of the solar wind. So you can calculate this by plugging in the light wave frequency redshift, and you can come up with the redshift by like what just spoken by. You had a furnace that you have a window on both sides of the furnace, and you heat these particles up where you have massive velocities of the particles. And since these particles are moving, they'll be moving to secondary sources. And the sources that are moving towards you would be redshifted up in frequency. The ones that are moving away from you would be downshifted in frequency. But coming from the other end, you have upshifted frequency and multiplied times 1 plus V over C times 1 minus V over C. What you get is 1 minus V squared over C squared. That's a redshift, no matter how you look at it. The higher the temperature you make, the greater this redshift is. And that is actually a redshift. You can plug in these equations, you come up with the bending effect. And that's easily calculated. You go to the website and I'll show you how to calculate it. You come up with this equation. You get a receding plus the effect of approaching, combine those two effects, and this minus a minus sign will cancel out, and you get plus, right? You come up with 4 GM over RC squared. First of all, each one of these contribute 2 GM over RC squared. This has a minus sign assigned to it because this guy is on approach. This guy is receding. This is plus GM over RC squared. Combine these two effects, you come up with 4 GM over R squared. And that's the bending based on the least time effect. Okay, so I'm gonna summarize what I have. This is summary right here. I'm gonna take one or two more minutes and I'm done. So what happens if you look beyond our solar system? This object is located some 26,000 light years away. This is the most intense observed object in our solar system. This thing has been looked at for, if you see this clock here, the time is steady. Started from 1992, coming up to 2000, what is it? 2006, yes, something like that. This thing has been, this image right here is about 10 years old. This thing today, this star has completed 1 orbit and it's on the way to the 2nd orbit right now, since we observed it. It takes approximately 17 years to make 1 complete orbit. This thing is called S2. It's on its 2nd orbit, and it's going to be in its 3rd orbit pretty soon now. So we looked at this thing, most intense observed object in the solar system right now. That's interesting. That's called S2. But look at this thing here. This thing comes in. It's called S3. That thing comes in so fast, and it looks around this object. Something is located right here. They don't know what it is. But whatever it is, they determine the mass of this thing. How to determine the mass? If you measure the velocity of these stars, and some of these stars are more massive than our sun. Some of them are 10 solar masses. Some of them be almost 20 solar masses. These stars are whirling around this thing. There's about 22 stars here. They're all on an elliptical path. All these things on Kepler path. Every one of them. And what you don't see here, you see no evidence of Einstein whatsoever. There's no bending, no lensing effect, no distortion of what's going on around here. But what's interesting about this star, this thing comes around, and when it whips around here, it's going 3% of the velocity of light. What did that tell you? This thing is going so fast, 3% of the velocity of light when it whips around here. That tells you, since these stars is massive as the sun, whatever this is, that's one of the best vacuums in the universe, right? Because these stars can move so fast. If there were any kind of dust particles or anything around there, these stars would disintegrate, right? That tells you this got to be one of the best vacuums in the universe. So what we determined, we have no light bending in vacuum space, only in plasma. Plasma limit the sun, where we have light bending, but out in deep space, there's no lensing whatsoever. You don't see any lens in here. But what the textbooks tell you is the following. That this is 26,000 light years away. And what you see here, this is what went on 26,000 years ago. So I'm just about done. This is the big thing blowing up. So what's happening there, you have this star coming in, and when it comes to near the after the distance of this whatever this is, it's going 3% of the velocity of light. So let me look forward on this. This is what you should see if relativity were correct. If relativity were correct, some of these stars would cause some lensing, right? And you just see that, right? This is what you don't see. This is in the textbook, but these are animated images of what relativity should look like, and this is what you don't see in relativity with this device. And this is in textbooks too. You see all these things all over the textbook. You see this image, the gravitational interaction, and it's just a black hole here, and that star passes behind the black hole. The light coming from that star should be lensed, or some sort of distortion should take place. And that's what you should see in relativity with the gospel. But this is what you do see. You see no effects whatsoever. Right? So let me go forward and I'll finish. This is what you should see also, no effect whatsoever. So we take the problems to give them to the students, and you have the mass halfway between the telescope and the source, right? And you have this bending, and this bending has an axis of symmetry. You take that axis of symmetry, I can rotate this thing around the axis of symmetry. This point will go over here, and that point will go over here. And this is a symmetrical bending equation that's easy to calculate. So let me click forward, and this is what we see. This is what we're wrestling with right now. You can calculate these things using lensing tools like this, and from infinity, these things come to a point at the source, right? And you have observer here and observer there. Both of these observers will observe lensing, but both observers will see something a little bit different. He will calculate a different equation than this guy would calculate, but both of them will calculate. Both of them will see Einstein ring. So I'm just finishing. So any questions? I can take questions if you have.
Yeah, we have 3 minutes for questions.
Okay. All right. So.
Is there a similar explanation for the alleged lensing by galaxies as opposed to the alleged lensing by the
that's
sun?
Very good question.
Microphone up to your mouth, please.
Yeah. When you look at galaxies, what they call lensing galaxies, there's a lot of objects out there that will cause lensing. Not only the gravity will cause it, but the lensing can be caused by the gases in space. It turns out that the mass of the universe, that is about 90% of the mass of the universe is not visible. What we see is only 10%, but there's 90% out there. But we know that when you get close to these galaxies, the region between the galaxies where you have bright images from it, you have scattering of light. And one of these is there's an X-ray scattering that is present. Yeah.
So a number of groups of astrophysicists were actually seeing much longer in the past than the current science admits, in particular
right.
the Big Bang and so.
Right.
So that is based on the gravitational lensing. So
Right.
how you would explain that? I mean, apparently we're talking about magnifying effect. So apparently they may be having that magnifying effect so that can see much farther away in the past than accepted.
They claim they can see. If these things were actually lenses, they claim they can see. But what happened? If you examine these images very closely, what you'll see is different wavelengths. If you put a filter in front of it, you filter out the optical wavelengths and you looked at only the ultraviolet and you looked at only infrared, and it's an entirely different image.
So I
That
actually
fails all the way.
I actually wanted to see if that is like fact.
That's right.
Would it even more support your insights and about just lensing as a refraction effect, right?
In fact, but relativity predicts the lensing should not be a function of frequency. It should be independent of the frequency.
Okay, this is
but if you look at the infrared only or the ultraviolet only, what you see is something entirely different. And all these things are laid to
We're
rest.
not really
when you do that.
to cross.
Anyway, let me skip forward and show you what's happening here. This Albert Einstein predicts. He said the velocity of light is not constant in all frames of reference. It's not tiny bit dependent on the velocity of light source. Then all my theories are wrong. And the list is from the fact to I claim Bishop. I think it from the toilet is systematic kinds of rock. So this like this in fast. That's what he said in there. So that's it.
One more question.
Right. so you just quote what he said.
Any more questions? No?
Yeah.
One more, that's
I
it.
didn't get the last word about gravitation and lensing. Does it affect the velocity of light?
Yeah.
The invent?
Yeah,
Slows
what
down.
you said, you have the light, electromagnetism of different wavelengths. Relativity predicts all wavelengths will be bent, right? All wavelengths, whether it's microwave, radio waves, optics, infrared, ultraviolet, all of them will be bent. So you can hold them to that, and you can look at these regions in different wavelengths, and what you see something different for all the different wavelengths.
Okay,
All that.
that's it. All right, thank you very much.